So with that, let me quickly, I know we're running behind, quickly introduce David. So David's an associate professor at Maryland. Before that, he was at Northeastern, and before that, Brandeis. David does research on lots of things related to types and contracts and gradual types, also abstract interpretation. And so again, what I love about David's work is that he takes these areas that are sort of foundational, like operational semantics or abstract interpretation, and studies them with kind of the aesthetics of our field, just kind of goes in and asks fundamental questions and discovers kind of great, simple, beautiful mechanisms that sort of were there in front of us all along, but we maybe didn't realize. And it's just, reading his papers is always a delight because they're so foundational and so beautiful. So today he's going to give us, I think, a sort of hands-on introduction to operational semantics, which is one of the kind of core tools that we use mathematically to reason about complex things like programming languages. So I won't take more of your time, David. Looking forward to what you have to say.
All right. Thanks, Nate. That was a very nice introduction. Let me know if you can't see the screen or see my mouse. So yeah, I'm not really sure if this is a mentoring talk or a technical talk. This isn't like an active area of research, but this is like a tool set that you basically have to have in order to sort of fully read ICFP or any SIG-plan papers, or most, I should say most SIG-plan papers. So if you just open up a random SIG-plan paper, you have a pretty good chance of encountering some presentation of operational semantics. So I just want to give you sort of an overview of what you're likely to find and the kind of notation that you'll see and the different choices that people make based on what they're doing there, okay? So the first question is, what is an operational semantics? It's really just a way of defining what programs mean, where the meaning that you give to programs is based on the actions that happen when you run them, okay? So you're writing down mathematically what it means to run a program, okay? And there's a bunch of different flavors of these, and I'm going to give you a taste of these different flavors today. So you might see something like an evaluator, where somebody writes a program that interprets programs that you're trying to define. You maybe see something like that in an undergraduate PL course. I would say that's kind of less common, although I did see there are some papers in this year's ICFP that have evaluator-based semantics where they give code for the interpreter. You might see something like a natural semantics, sometimes called a big step operational semantics. You could see reduction semantics, and there's sort of a couple different flavors here. There's what's called structured operational semantics or small step reduction semantics. We'll see those. Or you could see something that's really more of a low-level view, a kind of idealized low-level view in the form of abstract machines. And these are different ways of defining the operational semantics. Now, what are these things useful for? Well, you can use it to specify a programming language. So some programming languages have, spec documents that actually have operational semantics included in them. But really, I think the way that they're used within our community is therefore communicating language design ideas. And it's sort of a compact, concise way of communicating among experts what your ideas that are going on in your research paper are. And then, using that presentation to validate the claims, the scientific claims that you have in your paper. Often the sort of evidence that you'll find for these claims in a PL research paper are proofs about these statements that you make that often involve the operational semantics of a language or several languages or things like that. So, you could validate claims about type systems or program analyses or compilers and so on. And that's why you see them in PL papers. Okay, so Derek talked about this structure of papers that you'll often find, and there was the section that is, the least read section, which is the technical meat section. If you really want to understand what a paper is doing, that's the section that you have to understand. You have to be one of these 5 people that reads it and gets it. And if you want to build on somebody else's work, or you want to improve on something or apply it somewhere, this is really the part that you have to get through. And understanding operational semantics is sort of one of the key tools that you need here. So let's take a look at just a semi-random paper that I selected from this year's ICFP. I think this is coming tomorrow, called Effects for Efficiency. And if we look at the abstract here, it says, we study the fundamental efficiency of delimited control. Okay, so they're studying efficiency properties of some programming language feature here, delimited control. And specifically, they say, we show that effect handlers, so a certain kind of delimited control operator, enables asymptotic improvement in runtime complexity for a certain class of functions. Okay, so we consider the generic problem of using a pure PCF-like base language, lambda B, and its extension with effect handlers. Okay, so they've got 2 programming languages here. PCF-like just means it's like every other functional programming language you've ever seen, boiled down to its core. And then you take that core language and you add in this delimited control operator for effect handlers called lambda H. And we show that it admits an asymptotically more efficient implementation of generic count than any lambda B implementation. Okay, so that's a claim. Okay, that's something that this paper is setting us up where we're going to see this somewhere in the paper. There's got to be an argument for why this is true, and if you wanted to sort of make this precise, you have to talk about, okay, what are lambda B programs? How do they work? What are lambda H programs? How do they work? And how can you validate this property about this search procedure? Okay. So if you look in the technical meat section of the paper, they have an operational semantics for these 2 languages. And there's sort of this is the lambda B part, and then this is the extension for effect handlers, okay? So you can read the first, 4 or 5 pages of this paper, and without having any training in operational semantics, it's probably going to be, you can read it and understand what it is, the problem they're trying to solve, why it's important, and so on. But if you want to really get into why is this true and how do the details work here, you have to be able to read this kind of stuff and understand it, okay? And it's like this for many papers that appear at SIGPlan conferences. Okay, so I'm going to show you operational semantics in a setting that is just as stripped down and as simple as I can possibly make it. So our programming language here is going to be totally impoverished, but we're going to see all of these different things that you'll see in a PL paper. So I'm going to talk about a language of arithmetic. Okay, so just simple little arithmetic expressions. I'll show you the syntax, and then I'll show you the semantics in a bunch of different forms. Okay, including all the ones I've listed here. Okay, so when you're talking about the syntax of a language, so my language here is called A for arithmetic, you're defining a set. Okay, so you're defining the set of programs that are in the language. And I'll show it to you presented in a few different ways here. So one, if you wanted to be kind of super mathy about it, and you might say, okay, I'm going to define these constraints, and then the set that I'm talking about is the smallest set that satisfies these constraints. So you might say, so here are the constraints. If you have something that is an integer, so if I is in Z, well then that implies that that thing is in the language A here, all right? And if you have something E that's in the language, then then writing this pred symbol in front of it, that's also in the language. So this is a constructor, and we're saying, if something's in the language, then pred of E is in the language as well, and so on. Okay, so here's one with 2 sub-expressions. E1 is in A, E2 is in A, then plus of E1 and E2 is an A, okay? If you look at old papers, this is how they do it. You're more likely to see things written grammatically. So same information, same sets being defined here, but here we're using, you know, a sort of BNF style presentation. So here's saying what the integers are, and then here's saying what our language A is, and then you're giving a production for expressions E. Now, one thing that is a convention that we all follow that sometimes you don't see spelled out is that this is introducing these variables I and E, and those are meta variables that are going to be used throughout the rest of the paper, where they range over the things described by these sets. So whenever you see a variable E, maybe with subscripts or primes, you're talking about these kinds of things and nothing else, okay? So sometimes you'll see these and you should think of it as like, it's a pattern for saying, you know, one of these things, okay? The other thing that you'll see in papers all the time are inference rules. And inference rules are these things with bars where you see some stuff on top, sort of several different things on top, and then something down below. And this is just a kind of a 2D way of writing an implication. Okay, so you're saying these things are the hypotheses or the premises, and saying what this means is if these things are all true, then the thing on the bottom is true. The conclusion is here. Okay. So here's sort of another way of writing that those sets of constraints, but as inference rules. So if I is in Z, then you can conclude that I is in the set of things. If E is in the set A, then pred of E is in the set A, and so on, okay? Just a different notation, but this is a notation that you'll see all over the place, okay? And one of the things that's nice about the inference rule style is that you can write down proofs of things. So here is a proof that the expression plus of 4 successor of 2 is an expression in the language. And each of these lines corresponds to one of those rules that I showed you before. Okay, so if you wanted to check this proof, what you would just need to do is take this tree and look at all of the rules and make sure that it sort of conforms to one of the rules that I wrote down. Okay. Okay, so that's syntax. Let's start talking about what programs mean. And one of the kind of simplest ways that you can define the meaning of programs is by giving the natural semantics, or sometimes the big SEP operational semantics. So that's going to be a binary relation, okay, that is taking expressions in our language and giving you telling us what they mean. So here, our expressions are going to mean some integer. And here I'll write the binary relation infix here, and you might read this as evaluates to, okay? So plus 4 of successor 2 evaluates to 7, okay? That's an example here. And here are inference rules presenting the semantics for my little language here. So integers, okay, remember, I only ranges over integers here. So if you have something that is an integer, it evaluates to itself. That's what this rule is saying. And there's no premise here. This is an axiom. Okay, so 5 evaluates to 5. Let's look at pred. So if you have the pred of some expression, there's sort of a few different perspectives you can have on these, but you might read it kind of as, if you want to read it as how to compute what something evaluates to, you would say, okay, pred of some expression, well, figure out what that expression evaluates to. It's some integer I, and then subtract 1 off of it, and that's what pred of E evaluates to, okay? Or, you know, if you knew that E evaluates to I, then you know that pred of E evaluates to I minus 1. Okay, and successor, similar, plus it has 2 premises here saying, you know, E1 evaluates to I1, E2 evaluates to I2, then the whole thing evaluates to the sum of those 2 things, okay? So is it a set and an operator? It just, I mean, yes. Here we're defining this set, but we can also sort of view it more computationally. That if you tell me what expression you have, I can read these rules to figure out what the integer is here. Okay. And one thing that I think, you know, sometimes kind of trips up people the first time they look at it is, you know, just I want you to keep in mind that this thing over here, when I say plus, what I really mean is the addition of these two things. Over here, I'm talking about syntax. Over here, I'm saying, you know, you've got two numbers, add them together. And you might, if you wanted to be a little more explicit about it, you might write that as a premise, like this whole thing evaluates to some integer I such that I is equal to I1 plus I2. Okay. So here's, you know, a proof tree showing that that expression evaluates to 7. Okay. Okay, here's an evaluator. So this is an OCaml program that's really just sort of a transliteration of those rules that I showed you. So here I've got my data type for representing expressions, and then I've got a recursive function called eval that takes an arithmetic expression and gives you back an integer. Okay, so that's really encoding this binary relation as a function in OCaml. Okay, so it turns out that this is, you know, is not just a binary relation, but it's a function from expressions to integers. And then here we're sort of matching what we saw. So if you look at this, these things here correspond to the left-hand side of all of these rules. So there's one case for each of the rules we have, and then this is sort of telling you how you can compute that, where there's a recursive call for each occurrence of a premise here, okay? And then what's one of the things that's nice about this is, you know, this runs. You can type in expressions and compute the answers here. Okay.
Is a natural semantics the same as a denotational semantics, or is that something else?
So here it's sort of hard to tell. I mean, we're in such a simple setting that it's hard to make a distinction between operational and denotational semantics here. So here you might say that this is a denotational semantics because we're mapping expressions into some domain. Here the domain is integers, that's telling us what the programs mean. I would say most of the time, once you get into a more sophisticated language, often what you'll see here is something where, and by sophisticated I mean throw in functions or something, then this is really just the natural semantics is a kind of operational semantics. So it's giving you back usually some kind of like either piece of syntax or data structure or something that represents the meaning of the program. Whereas denotational semantics, usually you're talking about some sophisticated mathematical domain, and you're translating programs into that domain where you can use all of the facts of that mathematical domain to reason about programs. And that's a technique that used to have a lot of favor in the PL community, and I think sort of fell out of favor and is starting to come back some. Although I would say that the majority of papers these days still use operational approaches. Okay. Okay, so moving on to another flavor of semantics. Here is a small step operational semantics, structured operational semantics for the same language, okay? So I'm going to define this arrow relation, sometimes called steps to. And this is a binary relation, but it's not on expressions to their final value. It's to other expressions. And the idea is that this relation is going to spell out each of the steps of the computation. And something is in this relation if you can get from one expression to the other in one step of computation. So here's a little example of +4 successor of 2. This in one step, right? If we simplify one of the sub-expressions here, the successor of 2, that would give you 3. And then in another step, you could get from +4, 3 to 7, okay? So one thing to note here is that this relation is not going to relate the first expression to 7 because it doesn't get there in one step. So this is the one-step reduction relation. Okay, so usually there's sort of two parts to your one-step reduction relation. One part are the axioms. Okay, so here I've got some rules that look sort of like the natural semantics, or the big step operational semantics. But here I'm saying that if you've got pred of an I, so only like literally integers, if you have some more complex sub-expression here, this rule does not apply. So if you've got pred of some integer, then that takes a step to I minus 1. Likewise for successor, plus if you've got two integers in your hand, right, as sub-expressions here, then you can add them together. And multiply, you can multiply them together. Okay. So that's part one. Part two has to deal with where you can, which sub-expressions you can reduce here. So here there's a bunch of rules, but they're not saying a whole lot, okay? So if you've got a predecessor expression and the sub-expression can take a step, then the predecessor of the thing it steps to is what the whole thing is. So going from pred of E, you get to pred of E prime, you know, if E takes a step to E prime. And it's really just saying you can do one step of reduction inside of E. Likewise with successor, you've got two rules for plus, okay? So plus you can take a step on the left side, or you can take a step on the right side, okay? And same with multiply. Sometimes this is called the compatible closure, okay? Anywhere that there's a sub-expression, you can take a step inside of them, okay? All right. So these are the proof trees for those examples that I started with. Okay, so the first step, you know, because we can step from successor of 2 to 3, then plus of 4 successor of 2 steps to plus of 4, 3, and then plus 4, 3 steps to 7. There was a question about how does the natural semantics take non-termination into account? That's a great question, which obviously doesn't come up in this setting because our language is so weak. But that's sort of the main shortcoming of the natural semantics is it can't say anything about those programs that don't terminate. And that's one of the main reasons why you might use a small step operational semantics, is because you can still talk about all of the steps of a non-terminating program. Okay. Here's one of the things that kind of comes up here is that here I've got two different, I've got the same expression here, and I'm taking steps to two different things, okay? So the relation here is really a relation and not a function. And you might step to different things, okay? Now, it's a property of this language that whatever you step to, if you take more steps, you'll eventually get back to some common expression. But that's sort of one thing that can happen here. And then we can talk about a kind of derived relation, this arrow star relation, which is also a binary relation on expressions. And this is going to be sometimes called the reflexive transitive closure of the one-step relation, or the star should be sort of evocative of Kleene star here. And really what it's saying is you're in the relation if you can get from one expression to another in 0 or more steps, okay? So you can get from E to E prime in 0 or more steps if you can get from E to E prime in 1 step, okay? You can get from E to E in 0 steps, okay? So this is the reflexive closure of the underlying one-step reduction relation. And then here's the transitive closure part. So You can get from E to E double prime if you can get from E to E prime in 0 or more steps, and from E prime to E double prime in 0 or more steps. And now we can relate these two things that we've seen. So if something in the natural semantics evaluates to I, well, it should get to I in 0 or more steps. And this is a claim that you could sit down and try to prove both directions of this implication, which might be, if you're seeing this stuff for the first time, it might be a nice little exercise to try to do. Okay. All right, so we've seen two flavors, and now I'm going to talk about reduction semantics, which is really just a kind of a twist on the structured operational semantics. So if you think about the proofs for each step of computation in the small step semantics, they sort of always have this shape, where at the leaf you have some actual computation that's going on, where E takes a step to E prime. And then the rest of it is just building up that context that sits around that sub-expression that took a step, okay? So just to be concrete here, if you said that, this big sub-expression steps to this one because this inner sub-expression of 2 plus 3 steps to 5, well, the proof is gonna look like this, where you've got the 2 plus 3 steps to 5 here, and then everything else is just building up, the stuff that's sitting around it. So reduction semantics will often define a relation that's really just a subset of the one that we saw before, that's just the axioms. So the little a relation here is just the axioms that we had before. And then the way that you deal with this sort of building up the stuff around where an axiom was applied to is you'll define a grammar of contexts. So here I've got, I'm defining C as either this thing which is a whole, or the pred of a context, the successor of a context, and so on. Everywhere that I had a sub-expression, I've now said that you could have a context there. And then you'll see this notation C with bracket E. And what that's saying is, think of a context as it's a program with one of the sub-expressions missing, and that's where the whole is, okay? And when you see this, it's just saying, okay, you've got the context with the hole in it, and then E is sitting in the hole. So when you see this, you're talking about an expression, but you're breaking it down into some sub-expression, maybe buried deep inside of it, and the context around it, which you're calling C. So instead of having proofs that look like this, you will define your relation like this, where you're saying, if you've got some sub-expression inside of some context C, and that sub-expression takes a step by one of these reduction axioms, then plug that thing back into the whole in the context, and that's what the whole thing steps to, okay? And you'll see this a lot in papers because it's just so much more compact. And you don't have to write out all of these rules that aren't very interesting and so on. You just write down the grammar of contexts there. Okay, so, thinking about that little example that we did, the part in red, that's the sub-expression that is in the whole of this context. And the context is all this stuff that's sitting around there outside of it, okay?
Dave, I just want to jump in with a quick time check.
Sure.
We have about 10 minutes left, I think.
Yeah.
We started a little late.
Yeah, okay. All right, so yeah, let me move on from that. Another kind of variant, this isn't a different semantics, but one thing that a property of our semantics here is that you can reduce things, sort of in arbitrary sub-expressions. So you might not want that. You might want to talk about a particular strategy for reducing expressions, or you might want to determinize how computations go. And so this is sometimes called a standard reduction relation, meaning that reduction is standardized. There's only one way to do it. And here it is in SOS form. And the only thing that's really different here is that you've got this restriction on for example, on plus. So plus, you only get to reduce the right-hand side if the left-hand side is already fully reduced in an integer. So you're just sort of imposing an order here. Okay. You can also do this grammatically with context. So here is a grammar for context E that is restricted in the same way that those rules were, that is imposing an order of reduction here. Okay. So once you've seen, I think the first time you see these things, it can be pretty confusing, but once you get comfortable with them, you just read this and you say, there's sort of a way of reading this where you say, okay, in this grammar, the E's tell you where reduction happens in sub-expressions. So under preds, you reduce. Under successors, you reduce. Plus, you reduce on the left. Plus, once the left-hand side is fully reduced, then you reduce on the right. Okay. All right. Now, you can also have this claim about relating standardized reductions with the arbitrary reduction relation. So lets you reduce anywhere, and one that has a sort of predetermined order. And those, in this case, correspond with each other. You might want to have a more low-level view of how things operate. Okay. So here's a little abstract machine, a little stack machine. Okay. So I've got frames of my stack. The stacked frames are just going to be these very simple contexts. Okay. It's not a recursive definition here. They're just sort of constructors with a hole in them. Okay. And a stack will just be a list of those things. And then I'm going to define serious terms to be expressions that aren't integers. Okay, so these are things that need to be reduced further. And this machine is going to have sort of categories of reduction. One is you're doing some real computation, right? You have some expression under the current stack, and it takes a computational step, right? 3 plus 4, so on. You could have one where you've got some compound expression here that you need to reduce. So you've got pred with some serious sub-expression, not an integer, but something else. So you're going to push a frame onto the stack. Okay, so there's sort of push rules. You'll notice that these are axioms. And then there's pop rules that say, oh, I've got an integer as my sub-expression here, and the top frame of the stack is a pred frame. So I'll pop that frame off and construct this thing, and then that'll reduce. Okay. And you might relate, so I guess one thing to note here is that everything is an axiom here. I mean, with the exception of the reduced stuff, which are itself just all axioms, everything's an axiom here. So if you were to write this down as like an OCaml program, it would be a tail recursive OCaml function. In other words, it's just a sort of state machine, right? That's all it's looking at is the current expression in the stack, and it transitions to a new state, and then you just iterate until you've got an integer and an empty stack. Okay? And we could relate this to our other semantics about standardized reduction, and saying that E steps and 0 more standard steps to I if and only if the machine in an empty stack steps to I. Okay, so that's sort of all the different flavors here. Okay, that's like the basic structure of almost everything that you will see as far as operational semantics in an ICFP or any other SIGPlan paper, and everything else is just more cheese on the pizza. Okay, like it's all got the same elements to it. So you might throw, I'm going to go through this like super fast because I know we're short on time, but you might throw in syntax for functions and applications and variables, and you might have a substitution based semantics. So this is going to tell you what, when you're defining what application means, you use substitution to replace the argument with the parameter in the body of the function, okay? So this is the natural semantics for a call by name semantics. Here's the version that's call by value. Okay, so you have to evaluate the argument to a value first, and then you substitute that in. Here's what the reduction semantics looks like. So here I'm making this beta relation for, apply when you've got literally a function sitting here, then you do the substitution. You throw in some more context because we have new kinds of expressions, and you extend your notion of reduction to be, both the axioms of arithmetic and the sort of axiom of functions called beta. You could restrict it to be called by value. You could determinize the reduction order here by, instead of using arbitrary context, use only particular evaluation contexts. And you could do this for call by value as well. Okay. You could also make machines here, so you have some different stack frames, but it's still push, pop, and reduce, just like arithmetic, okay? All right, so you can throw more and more stuff on here. You want to do control operators, new expressions, new evaluation contexts, new axioms for how things reduce. The details here don't matter, right? You can get these slides and look at this stuff if you want. Call CC, whatever, okay? So that's just a quick overview of these different operational semantic sort of methods that you'll see. And one thing that, you want to sort of, this question of like, how do you deal with non-termination in the natural semantics? It's a great question because answering those kinds of questions tells you about what tool do you want to reach for when you're working on. So you might be in a setting where termination doesn't matter, and you can use the natural semantics, because one thing that's nice about it is you can prove things by structural recursion on the syntax of expressions. Or you might need to deal with non-termination, and you want to prove properties of programs that run forever, so you can prove things by induction on the number of steps that they take in the one-step reduction relation. Sometimes you have language features that are sort of context sensitive, right? They take into account where a sub-expression is occurring, and often using the evaluation context-based reduction semantics is useful for that. And in fact, when we look at this paper that I started with, which is dealing with control operators, so these things are sort of standard things. Some of them are just a little souped up version, like there's pattern matching in here and stuff like that. So it's got a few more things than we looked at. But then when we get down to the effect handler stuff, you'll notice here in this SOP rule, it's got an evaluation context with some sub-expression in it, and then that thing is being, is showing up over here, and so on. So they chose an evaluation context-based reduction semantics because it just turns out to be, very useful for presenting control operators that that deal with the evaluation context. There, okay? And this paper actually goes on to, because they want to talk about low-level properties of like the machines and efficiency and stuff like that, they use abstract machines in order to validate this claim about asymptotic improvements. Okay, so you've got these two languages, they present the operational semantics, they move on to the machines, and then they make precise what their asymptotic claim is and prove it. Okay. And you'll see stuff like this in many of the papers that you're going to see over the next 3 days. Okay. So that's it for me.